hardware accelerator, and click on save. So that's it. Here you don't need to install anything. You can just say import torch, and you can run. You can either click this small triangle kind of thing to run the cell, or shift enters the shortcut, and this perfectly works as your Python editor. This must be simple enough. Yeah. Can we do it in PyCharm? Yeah, sure. Actually, I'll be using PyCharm for the same. I'll just link the. You can just do pip install PyTorch. The basics one will be installed. In fact, you can do it on any, be it Atom, VS Code. For this, yeah, just type Google Colab. Uh, just type yeah, Google Colab, and yeah, so just click on this link. So you'll be prompted to this page, and click on new notebook. You'll be prompted to the same page. So you'll find if you're opening it for the first time, you'll find something known as connect here. So just click on connect, and that's it. You're done. You're all set for this workshop. If you want to install PyTorch, just go to the official PyTorch website. They have, if you have Anaconda, you can just type the command from their docs. That is as simple. I'll share the command if you want. Mm. Yeah, so actually, if you want to install it on your local system, I have put the link here. So select your system accordingly and which version of Python you are on, and if you have GPU on your system, just check for those, and you'll get a command below. Just copy paste it in your command window of Anaconda or pip, the normal command prompt which you use. You'll be good to go. Yeah, so I'll be covering the basics command, like not the much ML part. Yeah, and you'll an introduction to deep learning as well. The basic command, like not going in depth. I'll be covering that as well. So so the first session, I mean the first part of the session, I'll teach you how tensors work, and the basics before diving into deep learning. Then we'll build a very simple model which will learn something on its own. So I guess that should be a pretty interesting session. Yeah, okay, I will start the session now. Can someone say like what's the basic? So what's the first thing which comes to mind when you hear the word machine learning? Is it some sci-fi stuff or Iron Man? I don't know. Iron Man, okay. It's it's learning on its own. So, that's why it's all the hype, because before what we were doing, let's say you have to automate a task, you would, nitpick every algorithm, I mean, every aspect of it and write it yourself. You would give specific, commands that, okay, this is how you should do. But in machine learning, what you do is that you just say, hey, see, this is my input and this is what the output looks like. So you need to learn what's the relation between these, or how to get the output if I give you just the input. So that's kind of amazing. So if you go by the formal definition, the field of study that gives computers ability to learn without being explicitly programmed, as I mentioned. So let's say you are building a self-driving car. So, you can't hard code, let's say every if-else sentence that, okay, find a pedestrian, take left. I mean, that's just impossible to code manually. But if you use machine learning, you can, train the model, say that, okay, if you see a pedestrian, you're supposed to go this way, or if it's a green light, this is what you're supposed to do. So all those things, you don't need to manually sit and write the whole code for that. So that's something interesting. And yeah, so on a whole, this is what it does. So you'll have some sort of input, And usually what you for that input you'll apply some kind of rules or algorithms you to get the output which you want, right? So if you come to the ML domain, here X and Y can be any four of these, text, images, or videos, or audio file, or a tabular data, or basically a CSV file, or a number. So when I say text, I think when you open your Gmail, you can see different sections, right? Spam folder or social, like all the mails from your Twitter, LinkedIn, go to a separate one, and the important one come in your the first page of your inbox. So how that classification is being done. So input is a text here, and it's our it's segregating to either of the classes. So that is there are I think you would have heard about like GPT-3 models, or it can generate stories on its own. So you give a text, and based on that, so let's say an alien invaded the earth, if you just say that, it will continue the story for you. You can become a poet or a writer if you just build a ML model. And images, again, so for this actually, I would like to show an interesting application of that. Yeah, so recently, I think you've heard about DALI. So what this does is that you just give a sentence as an input. So here you say an armchair in the shape of avocado, and these images are not, picked from the internet. The AI is generating the image. So you can literally create any image you want, and you don't need internet for that, or So there was a API as well. Huh. So you can change any of these here. So let's say instead of a pentagon, I want a triangle. So these images, again, as I told, just from this text, no other data, just from this text, it's generating this, these images. So let's say instead of clock, a flower pot. So these are in form of triangle. So not just that, so many things are there. These animals. Uh, so I think that's pretty interesting. Where we have gotten from just building simple networks. Yeah, machine trying to optimize. Yeah, okay. It came to the section now. Okay, so yeah. So that was the basic introduction about what ML and what ML can do. And that was superficial. So to build this or implement this, let's see what kind of frameworks are usually used. I mean, there are two usually. I mean, the two most used languages. One is Python and R, but almost I could say more than 60 to 70% of the industry and in research, Python is preferred. So, I would suggest that you go with Python if you want to like learn this practically. So the helper libraries which are usually used are NumPy, Pandas, and Matplotlib. NumPy, to deal with all the matrix things. So ML at its core, it's like a computation of huge matrices. So for that, NumPy is used, and to handle data, Pandas is used, and to plot the data, to for you to get a good look at okay how my data looks and all. To for plotting, Matplotlib is used. So coming to the deep learning frameworks, the three most used frameworks are PyTorch, TensorFlow, and MXNet. So PyTorch is from Facebook, and TensorFlow is from Google, and MXNet, it's not from any company, but it was developed in a university with a bunch of students and the lecturer. Among PyTorch and TensorFlow, I mean, you can't both has on you can say 50-50 market. In research, usually these days PyTorch is preferred more, and TensorFlow is preferred in production level. If you know PyTorch, it's switching between either of the frameworks is really easy. You don't need to worry about that. I'll tell you one of the reasons why I picked PyTorch for this. Yeah, this is a meme I found. So, but actually PyTorch is more Pythonic. I could say, the classes it uses, and the flexibility it provides to you in what you can control in the deep learning model, that is more in PyTorch, I could say, and it's more intuitive than TensorFlow. And this is the Google search trends. Google, it has its trademark everywhere. So as soon as this is the TensorFlow graph. As soon as it came out, it got clarity increased. Now it has almost gone stable or decreased a little bit, but PyTorch, on the other hand, it's increasing slowly. And you can see in 2020 now almost they are at the same stage, but kind of it is predicted that PyTorch might take over because most of the research papers which are being released, most of them by either NVIDIA or any of these, the code for them is provided in PyTorch. So that's one of the major reasons for to see this increase in the graph. Yeah, so these are the few companies which are using PyTorch as of now. So I just showed you the DALI thing, right, or the text to image that is done from the company OpenAI, and they used PyTorch to build that model there. Mainly here, Tesla, you can see. Can you tell me for what Tesla will be using machine learning or AI? Open Pilot. Yeah. So this is a good talk by Andrew Karpati. Like he's the AI lead of the Tesla. If you're free, go watch on it. So here install introduction part. Now comes the actual learning part. One of the main things to note is that you can see that GPU usage is increasing more and more. Before, GPU was just used for gaming. The main usage was for that. But these days, the training of the model is preferred in GPU. So as this image depicts, this is from I took it from the NVIDIA blog. So CPU, it's like a jack of all, master of none. It can do all jobs, but it's not efficient at doing a particular job. But GPU, on other hand, it cannot do as much task as CPU does, but the task what it can do, it does it very efficiently, or else I mean it is designed to do very efficiently. So what are these boxes is that as you know that CPU has less cores, and the main reason I told that it can do more efficiently is that because GPU has many cores, so that all the computation can take place parallelly. So here, in CPU, it has to go sequentially, one after the other. It has to wait till that particular computation was done, and the next computation will be loaded. But everything at once can be done in GPU, so that's why it's much faster in GPU. If you hear things like GPU is it can be replaced by CPU. No, it cannot be replaced. So for that, I'll actually show you a quick demo video. This was by the NVIDIA. So just a quick video. It's a good one.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9,
9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Yeah, so I hope everyone enjoyed it and took the context as well. So this is what I meant. Yeah, I think we can get started with the actual stuff. Okay, PyTorch, I mean, when you're learning a new language or something, you go about the data types, right? The int, float things. So what is at the core of be it PyTorch or TensorFlow? That is something known as tensors. So a tensor is nothing fancy. You guys already know it actually. So this is a vector. This is a matrix, and so any matrix or any tensor which has more than two dimensions is generally considered as tensor. So you can see when you are doing deep learning stuff, you can easily deal with very high dimensional tensors, be it like hundreds or thousands together when the data gets really complex. So this is a nice so what you can see is a nice way to express how or to visualize how higher dimension tensor could look like. So have a look at this. So okay, so let's do that. Let's create a PyTorch tensor. For that, uh, okay, I'll be sharing my whole screen. You can open your Google Colab or your any Python editor in which you have installed the PyTorch. Or for the people who join late, just go to Google Colab, click on connect here. This will take you to just go to Google and type Google Colab. It'll take you to this URL. Click on new notebook, and just you'll see something as connect here. Just click on connect. You don't need to install anything on this. It's just another tab on your browser. That's the best part. And just go to runtime, change runtime, and click on GPU. The one which you just saw, just to accelerate things faster. Yeah. Even though NumPy is a famous library for doing all the matrix operation, however, PyTorch is preferred over NumPy here because the normal operations can be done on GPU using PyTorch. But if you use NumPy, you have to do it on CPU. It doesn't support GPU. So that's one of the main reasons. Again, PyTorch is one of my favorites. So, okay, let's get started. So first we'll import the module, that is import torch, and I always had the habit of doing import PyTorch, but it's not PyTorch, it's just torch. I don't know why they made this. Okay, so first let's create our first tensor. Let's say okay, t equals torch dot tensor. So the first argument will be the number, or what's the element you want. So you could give it in multiple ways. You could give it as the list. I mean, Python list general. So let's say 1, 2, 3, and you can anyhow specify the type of the elements as well. So let's say uh, yeah, okay, D type. I'll make it float. So let's say float 16, and let's print this. And for PyCharm users, Shift F10 will run the um, code for you. So that's a shortcut. Um, yeah, so you can see, even though here I've just given integers as the input, since I've specified the D type to be float here, that's why I'm getting 1.2 here. So let's say I'll change this to int int 8, let's say. So I'll run this again. You can see it's just 1, 2, 3 here. That is good. So here, this is just a one-dimensional, or I mean, basically a vector. If you want to manually type two-dimensional vector, so what you would do is that first, just keep it, put a list in a list. So let's say 1, 2, and another list here, 3 comma 4. So this will be a two-dimensional tensor. So you can see here the format has changed. So anyway, so if you want more dimensions, just keep on including lists within this. That will do. So for this, let's say how to check the shape of this tensor. Let's see t dot shape, and see this is 2 comma 2. That is correct. And if you want, so by default, what happens is, if you don't specify anything, this will be on your CPU. If you want to shift it to the GPU, you have to say device equals, and in as a string, give it CUDA. Since it's initializing now, it will take some time, but yeah. So now this is on the GPU. This tensor is on GPU. How do I check that? So I'll just say t dot device, and is it slow? Yeah. So this number, what it specifies is that if you have multiple GPUs, it will show in which GPU it is. Since I have just one, so it's showing 0. So this is how you create a tensor. The basic core of PyTorch. What's the numerical suffixes to the data types? You mean torch int float? That's what you mean? Numerical suffixes. Okay, so when he answers, I'll get back to that. And so first, let's see how we can create different types of tensors here. Basically uh, initializing a tensor. Okay, so let's say t equals torch dot once. And the first argument will be in the tuple. You have to give the shape of the matrix. So let's say I want it to be 3 cross 2. And let's print this and see. I'll just comment this so that it doesn't take much time from next. Yeah, so you can see the first argument, you can specify how many rows you want. So since you've given 3 here, you can see 3 and 2 for the 2 columns. So instead of that, if you give zeros, that will be, you'll get all zeros again. And if you do I, you'll get a diagonal matrix where all the elements of the okay. So here the argument type is different. Just a second. Yeah. So okay. So this needs to be a square matrix to realize that. So except the diagonals one, everything will be 0 as you can see here. Only the diagonals are 1. So this is torch dot I, and if you want to initialize this with a random number, you would say ran n. So this would pick from the uniform distribution, and this will give you a random one. But if you okay, let's do this one. So you can see here, I have got a matrix of random number of 3 cross 3. But let's say you don't want float and you want int in this. So what you would say is that rand int, and here the arguments are different. In the first one, you have to say what will be the starting. I mean, what's the minimum value you want in your matrix. So let's say the minimum value I want is 0, and what's the maximum value I want in my matrix. So let's say 10. So no elements in my matrix should be larger than 10, and now comes what's the size of the matrix. So again, let's say 2 cross 2. I'll run this and uh, okay, yeah, I think it should work. Yeah, so you can see none of the elements are, they are not crossing this, and you can give this any shape you want. So that is about the initializing. And one more thing, let's say, when you do in for loop, you say for I in range, right? So a similar uh, method is there. So that it is dot a range, and you just give any number. So this works exactly how it works in the for the range function in the Python. So yeah, I've given 21. You can see it same like that. It doesn't include the last number. You've got till 20. So yeah, so you should know these basics before we go on to doing any fancy stuff. Any doubts till now? Okay, int 8. That specify what's the length of the int you want. So I don't remember the numbers exactly. So let's say int 8 takes 32 kilobytes. Int 16 will take maybe 64 kilobytes. It will increase the amount of memory it's consuming. So if you're specifically specifying 8 or 16, you need to be you have to good no you have you need to have a good knowledge of what exactly or what's the size of your data. What exactly is a tensor? Yeah, so tensor is that's what again I said. Tensor is nothing fancy. Vectors and matrix, right? Vectors are one dimension, and the matrix is two dimensional. Something which is let's take a 3D or an image is a three dimensional matrix. So any matrix which has more than two dimensions or stacked up together. So let's go to this presentation. Yeah, so you can see what is this 3D tensor is that this 2D tensor is stacked one by one together to form a 2D tensor. Same way how if you concat so many 1D layers like this, you will get a 2D tensor, right? So if you concat 2D 2D matrices like this, you will get a matrix like matrix of three dimension. So that there, just giving it a fancy name called tensors. So, if you know what is matrix, basically you know what is tensor. Nothing fancy in that. I hope that cleared your doubt. Okay, cool. So, okay, let's move on to further ones. So we'll see how to do basic operations in tensor. So let's say x equals torch dot tensor, and let's say 1, 2, 3, and torch dot tensor. Yes, 5, 6, 7. Okay, so I'll just keep on commenting. Huh. So how do we add these? It's simple. The notation, x plus y. So there you go. This is 6, 8, and 10. Minus uh, again. Fair enough. Yeah. So now comes the tricky part in even the summation. Okay. So instead of this, let's take uh, random and let's have a three-dimensional matrix. So let's say 3 comma 2 comma 2, and yeah, uh, okay. No, actually, I'll 1 minute. Yeah, so if you want to do torch dot sum of x, and just a minute, I'll just explain what I'm doing. Okay, I'll use this one. This will be better. Yeah, so you can see that this is the tensor I'm just printing here. This is a three-dimensional tensor. So uh, the first dimension specify what is the number of channels or the depth of this. What do I mean by depth? Like, how many 2D tensors you are stacking up. So you can see that 7, 8, 7, 1, 0, 6. These are the 2D tensors, and since I've given three, I'm stacking three 2D tensors together. And 2 and 2, it means the usual, the rows, and the 2 here is the rows, and 2 here is the column. So let's say I'll say here just 2. You can see that I'll just get yeah, I'll just get 2 here. So, because I'm saying that I just want to stack up only two tensors together. So here, so let's say I have a matrix and I want to do internal addition of it. There is three ways I could do it. So by using this method, torch dot sum, the first argument is the tensor, in which of which you want to take the sum of, and this is called the dimension. So dimension means that along which dimension you want to sum. So here I've given 0, right? So according to PyTorch indexing, this is 0, this is 1, and this is 2. So the indexing goes as per the dimension 0, comma 1, comma 2. So 0, since it's the depth, it's going to sum all the tensors along the channel. You see, so 8 plus 0, this is the channel depth, right? So 8 plus 0, that's why you have 8, and then 9 plus 9, 18, and 2 plus 3, 5. So when you say 0, you want to collapse that particular dimension. So this 3D tensor, now it's collapsed into a 2D tensor because you're adding along that dimension. Now if I say along the first dimension, that is the rows, what I can expect is that all the rows should be collapsed. What so it should happen is 8 plus, I mean, yeah, here 8 plus 2, I should get 10, and then 9 plus 5, then again 0 plus 3, and 9 plus 3. So that's what I expect to happen. Let's see. Yeah, since I've not set, okay, this is our new set. So you can see 6 plus 9, 15 I've got, 5 plus 3, 8, and 7 plus 0, 7, 2 plus 1, 3. So hopefully I've cleared the dimension part, because this might seem like a small thing right now, but when you'll be building, this is where you get strange bugs, and you won't, it will be difficult to debug. So I hope you got the dimension concept. And if I say 2 here, 2 is what? The column 1. So along the column, it will add, so it will be 6 plus 5 and 9 plus 3. So let's change here and see that this works. Yeah, so you can see 7 plus 5, 12, 3 plus 0, 3, 3 plus 1, 4, and 4 plus 3, 7. So, okay, so moving on to the next operation, that will be multiplication. So, here you can do two types of multiplication. One is which you do element-wise multiplication. What do I mean element-wise? Like you just multiply, 7 into 3. 5 into 1, 3 into 4, 0 into 3. So that is element wise multiplication. And the normal one is, remember, we learned it in our PU class, that if you have a dimension of m uh, of what? Okay, m cross n, and if you have another matrix of n cross p, if you multiply these two, the output will be m cross p. Yeah. So basically, we can do both kind of additions here. So let's take another, let's say x equals torch dot, and then let's give it 3 cross 4, and y equals torch dot random, 4 cross 5. Note that the number of columns in the first matrix should be equal to the number of rows in the second. That's the basic one. Basically, the n here should be the same. So you can do, you can call uh, math multiplication, and you can just pass the two matrix. Okay, so let's comment this out for now. Yeah. Uh, so let me drag it here. You can see that 3 cross 4 and 4 cross 5 means I should get the output 3 cross 5, right? So here you can see there are 3 rows, and you have 5 columns here. So this is how it works. And if you, let's make this to have element wise multiplication, it's advised to have the same dimensions. So let's say I just give x, y. The normal convention will give you. So let's do both here and see the difference actually. So that torch dot and x comma y. Yeah, so you can see here, right? This is the element wise, and this is the matrix multiplication. The actual, I mean, the technical matrix multiplication which goes on. So the answer here are different. So just to prove that. So just in case if you do this, you might not get the results you wanted. So that is about multiplication here, and so add, multiply, that is done. And uh, okay, you guys remember dot product. So basically, if you have two tensors, let's say this is one tensor and this is another tensor, the dot product would be corresponding multiplications, and if you add it up, you get the dot product, right? How do I take this? I mean, without coding it manually, I could say torch dot, and one thing to note is that torch dot dot, it only works on 1D dimension. If you give x or y, because since this is 2 dimension, this will give you an error. So let's say torch dot a range from 3, and yeah, so it will multiply and give you the same answer. So 1 plus 1, so 2 plus 2, and 3 plus 3. 1 into 1, 2 into 2, and 3. So that should give you the answer. So next, moving on. Okay, so let's see few more operations. That is how to take absolute value. So in this, so if you print x here, you see it even has negative numbers, right? So let's say you want to remove all the negative values of this. So how would you do that? That you do print torch dot absolute value. You will pass x and yeah, you can yeah. First I'm printing the absolute values, so you can see the negative ones here. They are returned as positive ones. That and let's say here um, instead of say taking sum, we summed it across the dimensions, right? But if what if you wanted to take maximum value among these three or that same same thing. So here you would say max and you would pass the tensor and you would say across which dimension you want to take the maximum value because it will differ, right? I mean, do you want to take the maximum along the rows or along the column? So zero means rows, right? So I should get okay. Yeah, so along the rows you can see this is first one, this is the highest one, and this and one thing special about is that it also returns the indices. You can see that here yeah, okay, sorry, one thing, zero rows means the rows will be collapsed. So if the rows will be collapsed means that is across the columns, right? So it even the highest value is in the last row here, that is 2. Here it's in first, here it's 2. So one good thing is you can say uh, val and index, you'll get both the value and the index for this, standard tuple unpacking here. So if you don't want the maximum, if you type min, you'll get the minimum along the rows. Yeah, I didn't print this, but yeah, you get the point. So this was again basics one. Mm, okay, now let's go to how to reshape matrix because this is mostly used because the data set will be in some weird shape. You have to feed it into a model, PyTorch. It expects that it should be in a particular dimension. That all the data set should be in. I mean, all the data examples should be in the rows. All the features should be in the column. So for that reshape is very important. So let's say here t is equal to a range and it has 9. So let's just print just to see it and comment others. Yeah, so you got 9 values here. So let's say I had to reshape this into 3 cross 3 matrix. So I could do it in two ways actually. So one is reshape and I could say 3 cross 3. Let's do that. Um, yeah, you can see here 0, 1, 2, 3. Now we have it in this format and you also can do dot view here. I'll tell you the difference between these two methods. Yeah, you got the same output, almost no like visible time difference or sensible time difference. But why view works? I mean, the main advantage of view is that it works. Actually, it might not be noticeable. It's faster than reshape because view works only on contiguous memory. I mean, continuous memory. You guys know that memories are usually stacked in the form of matrix, and arrays are continuous arrays, and linked list. You know, it's not continuous. You have a piece of memory here and there. So how this T-torch tensor is saved in the memory. Sometimes, if it has enough memory, it will be saved continuously, or it can be saved as chunks of, let's say this row is saved somewhere else, and this row is saved in some other part of the memory. Then T dot view will give you an error. And there are some like methods which, even though previously if it's a continuous memory, it will break the continuity of that. So let me do here T dot T. So this is the transpose of the okay, no, here I should, I mean, yeah. So this is taking the transpose of the vector, and let's print that to see that this works. Uh, yeah, so you can see it has yeah, transpose of this vector. So the it has gone to its initial state. Now if I see if I do is continuous, it will um, wait, 3 cross 3 yeah, yeah, I think A range, it has some other format, but usually the tensor in, I mean, its form in the random form, you can see that here it's not contiguous anymore. And this transpose operation, it has made the memory allocation not continuous. Now if I try to uh, run this operation, it will give me an error. Let's say I want to make this as a simple. Hmm, hmm, okay, I'm not returning it here. So yeah, so you can see that view side is not compatible with the tensor side, and one dimension spans across, and see, and it says it you can see the error here. Um, See, it's telling you that, and across two contiguous subspaces, it's not that anymore. But instead of that, if I use reshape, um, see, I got the output. So this is where you have to be careful. I mean, always use reshape for to be in the safer side. But if you want to optimize your code along with that, be you can use view, but you need to be careful about that. So that was one main thing to notice. Um, and another, I think that's it for now. For the basics of tensor, any doubt you have? What's the difference between a vector and an array? Okay, so a vector is something which has just one dimension. This like 1, 2, 3, or it's here. So this is just a one-dimensional array, one dimension, because uh, like it is stacked along just a single dimension. So let's say you're consider a road that is just one dimension, right? Because let's say you can stack the numbers only on that particular that particular row. But let's say you take your table, you can stack it along horizontally and vertically as well. So that is a matrix. The basic vector, I think you would have studied in your PU, the same definition holds good. Yeah, vector is a 1D array. A matrix is a 2D array. And tensor is three dimension or more than three dimensions. Yeah. Mm, okay, cool, cool. Yeah. Uh, okay. So, so now coming to a little more interesting part, how to take gradients. PyTorch has something known as autograd package. So it'll let you do it'll let you take the gradients. I mean, take make differentiation possible in code. So let's see how to do that. Mm, in the same way you did this tensor. Let's take the same one here. And here, I'll say require radicals true. Um, yeah, just bear with me for a minute. So, so what this allows me to do is that if I this parameter requires grad, it will let me compute the computational grad. So what I exactly mean is that the PyTorch, so whenever you form a variable, let's say x is equal to 7 and y equals 8, and you add the thing, it forms an internal graph like this. I mean, that's how things work in backend. So if you want the connectivity to be held for calculating the gradients, yeah, actually before that I go, I hope everyone remembers what are gradients, or like what's the significance of the physical significance of gradients. Slope, yeah, correct. It's the slope of equation. So I mean, you would have heard that, right? Deep learning, it has a lot of math and it has a lot of calculus and all. So you do need to, calculate gradients while building your model for any application. So how do you? PyTorch allows you to do that very efficiently. I mean, with so much of ease. So for that, to calculate that, if you give this argument as requires grad equal to, it will start forming this graph. So here, okay, let's make it x and y. Okay, let's not complicate stuff here. Let's just give a single number. Um, 4. Yeah. Oh, huh. So let's say I'll do x plus y, simple, yeah, x plus y. Um, so can you tell me if I do dz by dx, what will be my gradient? So I'll show you again. So just simple one, just to jog your memory, so that this is x plus y. What if I do dz by, okay, this is dz by dx.
dy by dx.
Yeah, correct. Dy by dx. So here, okay, if you consider, I mean, for the PyTorch, this will be again a constant, right? So this will get cancel. I mean, this will be 0 since this is a constant. I mean, while calculating this, PyTorch will substitute this as 4 here. So this since it's a constant, its gradient will be 0, and dx by dz will be 1. So the answer should be 1, right? So how to calculate? So we have um, so we have come, we have done the computation graph till here. Yeah. So if I do z dot backward, and if I print x dot grad, let's see, I should get 1 here. Um, Okay, yeah. So one more thing to notice is that PyTorch allows you to calculate gradients only on floating numbers. So let's say 3.0 and make this 3.0 for that. For us, it's easier. Mm, yeah. So you can see the x dot grad is 1, and similarly y's should also be 1. Yeah, it is 1. And if I make here 2x, the answer should be again 2, right? So, just cross-checking that this z dot backward actually works. Oh, yeah, this is of y. Yeah, see, you got 2 here. So, you are convinced that the normal method, of calculating the gradients, you just define the equation which you want, and you call z dot backward, and it does the job for you. So let's say I'll set this to false, it will give you an error. Because every time it doesn't do, because obviously it takes up time and uh, uh, like space to do it. So unless you specify it, by default, the required grad will be false. So you can see since this is true, it has given none, or if this was also false, it should give an error. Yeah, you can see element of 0 does not require grad, have grad function. And one more thing, if both are true, the required grad for the z will automatically set to true. So z dot require grad. Let's check that. I have not explicitly set something that z require grad should be true, but since both x and y have it true, it should also have its gradient require grad set as true. Yeah, see, you can see that this is true. And one more thing. So actually, let's complete this computation graph which we have here. So after that, let's say a equals set into 4 and b and c. So b equals 2 plus a, and c equals 6 into a. So this graph which I have defined, it's exactly the same. You can check x plus y. I've made it one. I mean, any operation into z, and from z to a, from a to b, and a to c. So one crucial thing to note about is that. So let's say I'll do b dot c. I mean, sorry, b dot backward. Um, so now you got your gradients computed for x and y. You'll get the gradients will be stored if you do x dot grad, if we saw. Now let's do c dot backward. Something interesting happens right now. See, you get an error. It's not that it's because of C, because C's initial or lateral interchange the uh, order as well. Mm, see, you got an error in B dot backward, not C. So what usually happens is that so once this computation graph is formed, if I call B dot backward, this whole computation graph gets collapsed. So this whole connection to C, this graph gets collapsed. And if you say C dot backward, it doesn't have it. That graph is gone anymore, so you cannot compute the gradients. So that one thing, you need to be very careful about. If you have some structure like this and you want to compute gradients from with respect to B and C, but what if you want to do? There is a solution for that. You can pass a parameter called as retain graph equals to. But again, as I think you would have figured it out that. The retain graph parameter will be um, by set to false by default. So let's run this now. See, you didn't get an error. Both C dot backward and B dot backward are computed. So, and another thing, let's say you don't want any particular variables gradient to be computed, because sometimes what happens is computing gradients of a really large networks will take up too much time. You know that this gradient is not required for me, but it's already there in the computation graph. So what you can do is that you can call z dot detach. So now if you print set dot grad, it will not have any hmm, um, let us pay let me faster. Um, okay, one second. Okay, so element 0 does not require grad, and um, yeah, so you can see that z grad is returning as none here, because I've put detach on y, and the corresponding gradients will not be calculated. Yeah. Any doubts till now? X is also a constant. Uh,
Yeah, I asked
yeah.
that when you first did the z equal to x plus y.
Uh,
You did
hmm.
you asked what would happen if we did dz by dx. X would
Hmm.
also be treated as a constant, right?
Um, Not exactly. See, if you do x plus y for this, I mean, it will consider the variables. I mean, like, don't get into multivariate, calculus as of now, because usually what uh, variable it is, taking headache with, only that, it's going to consider as a variable, and everything will be treated as a constant. So that's why y will be a constant here, and since I'm doing dz by dx here, my x will be treated as variable, and dx by dx will be 1, and you will get 2 as your output.
So basically partial differentiation, like that.
Basically,
Partial differentiation.
Yeah, that's what I mean. Partial differentiation. Yeah, don't. Yeah, correct. Exactly. Yeah, partial differentiation. You can say. Yeah. Mm, yeah. Yeah. That's some better explanation. So that was the basics of all the tensor, or I mean all the things you need to do. We can start building a very simple model. Uh, if any other doubts you have, we can take maybe a 2 minutes break. You can play with something and see if you want. So what we'll be doing is that we'll expect, the ML model to learn uh, the sine function on its own. So first we'll go through the theory of that, and then we'll do the coding part. Till that again, any doubts again? I'll just turn on my charger. 1 second. Hmm. Okay. Uh, okay, we can start with the theory. So, all the uh, like the magic unfolds. Okay. So, huh. So we'll try to do a very simple thing right now, because like since most of you are new and directly jumping into some real world data set or something can be confusing. So let's do simple one. So as I told before, this ML, how it's different from conventional programming is that you say, okay, hey, this is X. I mean, this is X, and the answer should be, I mean, the corresponding correct output is sin X. You just feed. I mean, this will be always like different values, so 1, 2, 3, or pi by 2, pi by 3, different values of X, different pairs, and you expect it to learn this sine function. So here it's something simple as sine. It can be any complex function if you want. Obviously with the complexity of the architecture increasing. So this is the overall thing we need from ML. So let's see how on a surface level it does that without banging our head too much. So the first step is known as forward propagation. What it does is that, let's say x, this is pi by 2, let's say, and there is something called as neuron. So people usually take this example that that the more neurons we have, the more neurons and more neurons connection we have, that is equivalent to our cognitive abilities or memory of our brain. So similar way, in an deep learning model, the most elementary thing is a neuron. So that neuron here, what it consists of, something known as weight. So this weight is nothing but a number. It's literally a floating point. That's it. They've just given a fancy name as weight. A neuron consists of weight, and sometimes it consists bias also. So here, for simplicity, we'll just be considering the weights. So this will be pi by 2. This weight will be initially some random number, let's say 0.2. You multiply pi by 2 into 0.2 and you'll get some output. Let's call that x cap or x hat. So that is the first step, in training our model or in the process of our machine learning. Then after that, in step 2, you'll calculate the loss. Basically to tell, because since initially this will be a random number, um, it has to reach a particular value in which the loss will be minimum. So what do I mean by that is that x cap minus, this is the actual value, right? I mean, x sine of x is the actual value. This is what I want as my output. That I'll if I minus this, I mean, if my network is proper, I should get a loss as 0. If it's not, the loss will be, I mean, basically it will not be 0, and I'm I mean, I'm making this exponentially to the power of 2, because even if it's 0 point, okay, I mean, even if it's a a small number, if I square it, the value of that will become large. So x cap is, just multiplying x into w, the torch.mm which you saw, that is just literally this thing. And if you minus this with the actual value, that's how, and you raise it to the power of 2, that's how you calculate the loss. Then the third step is calculating gradients. As I mentioned, that's one of the important steps. So what you do is the loss which you found out here, you can see that in this loss equation there is weight, right? This is what we want to minimize here. What I mean is that our aim is that our loss should be in minimum, right? So for that, I'm trying to find what's the optimal value of W which will give me the minimum loss. That's the best model I can train, or that will give me the most closest prediction of the actual sin x value. So to do that, I'll take the gradient of that with respect to the weights, and that gradient value, I'll subtract it with whatever the current weight it is. So to give you more intuition on why this particular thing works, so let's look at this graph. So here are different values of weights, just plotting this equation here for different values of weight, what is my loss? So this is the usual function, which we get here. I have to find the minimal loss right here. The loss at this particular point is minimal here. So I mean, as I told, the weight will be randomly initialized. It can be here, I mean, here in the sense here or anywhere in this. But how do I bring this weight to my minimal point? So what happens is when I take the grad, that is basically, as he told, this is the slope. So here, if I initialize here, the slope is positive, right? So if the slope is positive, then W minus some slope will be my new value of weight. That means I'm moving this side here. Like, if my value of the weight is decreasing, the loss is also decreasing right here in this direction. So as you can see, if it's here, the slope is reducing. That if the slope is positive, that means I'm reducing my weight, and I come to my uh, minimal position here. But let's say, what if I initialize my network to be somewhere here? That means the slope will be negative here. If you can imagine it, right? Tan x by tan, that uh, yeah. So if the point is here, the slope will be negative. If the slope is negative, negative into a negative of something will be plus. So whatever the value of weight here, I'll be adding the value of the gradient. So value, if it's here, means my value is too small, right? The value of W. So I'll be adding the value of grad. So that means I'll be progressing in this direction. Again, coming to minima. So if you want a high level intuition of that, if this is a valley, and if you drop a ball here or anywhere, it will usually come to the minima part. I mean, this is where the gravity energy will be low, right? I mean, the potential energy. What was that equation? Mgh something height. Yeah. So basically, what I mean is that uh, no matter where you live, you start the ball with, you will end up here. That is for sure, right? So so the same intuition or the concept is being used. So once you reach here, you can see that the loss will be minimum. If the loss is minimum, can you tell me what will be the slope of this when the loss is minimum? What will
Zero.
be? Yeah, exactly. So if it's zero, that means my grad will become zero here, and my weight will be weight. So if you check that, okay, my weight is not changing, then that means okay, then I have reached my optimal weight. I mean, this is the best weight I can get for this neural network. So that's how we are convinced with this. I hope I made this clear with you all. We can simply take the limit loss to zero. Uh, I mean, is, I mean, taking limit is same as slope, right? I mean, if you take the physical significance of limit or taking the gradients, it's the same, right? So that's I mean, what is differentiation? When the limit tends to infinity, okay, infinity, when the limit, no, when the step tends to zero, that is what is differentiation, and that's how we are calculating the gradients, right? So, um, I think it's yeah, it's the same concept which we are following here. So this is all the theory part I have, and we can start coding. You can open your coding environment again. You can code along to see. So fun part is what I'll get the results. You might get some other different result. So it's not fixed that okay, this particular number has to be weight or something. So, to give this a high level example, you can think like every person has his own perspective of like perceiving things, right? So, even a different neural network, I mean, even though it has the same architecture, the weights will be different, or you can say that the perception of that model will differ from one model to another model. So, you can try, you might get a better results or not so better results. So it would be fun if you do. So let's import torch and from just a second. Yeah, so once you have just done the import torch and the environment is ready, just let me know again. You can code along with me here. Copy the code and yeah. So I'll tell you why this imports are needed, and then okay, first let's make our data set ready, set of x and sin x. For that, let's say x dot torch dot lens space. So the first argument which you give, uh, that will be okay. I'll just write it and explain it later. let's see, 500. Okay. So what this start.len space is doing is that this the first and the second argument is the start, and I mean this is the minimum and maximum value of the 10, I mean of the elements of the tensor. And this 500 means that between this range I want 500 elements. So let's say this is so to give you an example, so let's say this is 1 and 10, and if I say I want 5 elements, it will equally divide the 5 elements from 1 to 10. So your elements will be 2, 4, 6, 8, and if I put let's say again 10 here, I'll have 1, 2, 3. If I give 2 here, again 2 elements equally spaced, that will be 5 and 10. So similarly, from this range, I'm multiplying it by pi because since I'm doing it for the sine function, I'll have absolute values and I'll get a smooth sine function. So let's pass it to the sine function. So let's plot this and see that uh, am I getting the correct graph? For that, just say plt dot plot. The first argument will be what you want to plot in the x-axis. In the x-axis, I want the arguments, and y is the sine function of the x. So let's run this and okay. Hmm, okay, torch doesn't have pi. Uh, okay, then maybe I need to import. Okay, wait, let me just Google it soon. Because I think some um, hmm, okay, this is complicated. Maybe okay. So torch doesn't have one that. So let's do this with numpy array with numpy has this. So basically, np dot pi is 3.14 with precision. So let's run this now. Mm, okay, this was in the. Okay, if you do it in Collab Notebook, this should show up actually. It's not, but like if you plot it in the Collab Notebook, it should. So let's just quickly uh, do this here. Yeah, so you can see, yeah, we've got uh, the sign output for this. So our data set is correct right now. So let's see what's the shape of this x. So let's say x dot shape. It says 500. Basically, it's saying that it's a 1D tensor. But what PyTorch expects is that the input always, no matter what it is, the input should be minimum two-dimensional. So what I could do is that instead of 500 comma 1, I could do 500 instead of just 500. I could put another dimension saying 500 comma 1. So that's again the same vector, but the dimension according to the PyTorch will be increased from 1 to 2. So how do I do that? I say x dot x equal x dot un unsqueeze and um, 1. So now if I print the shape of x, oh, this uh, you can see it's 500 comma 1. So what this unsqueeze does is that it adds an extra dimension for your data set. Since it was here 500, right? And what is this 1 or 0 along which dimension I want? 1 means column, so it's adding the dimension across the column. If I make this 0, it will add it along the row. So my thought I mean, this x shape would be 1 comma 500. Let's just check that. Yeah, before, since I had done that before. Mm, yeah, you can see that 1 comma 500. That's what you're getting. But let's change it back to 1. And as I mentioned, the gradient autograd, it only works on the float. So this dot float, this method converts it into float. And let's do the same for the um, y as well. So again, since it was here 1 comma 500, again like since this is a Jupyter notebook, basically it will keep in mind the previous output. So if I do for 1 comma 500 again unsqueeze dot 1, I'll get 1 comma 1 comma 500 as you saw. That I don't want, right? So I'll just rerun this cell again so that my inputs are set again. So yeah. If you want to check the Y shape for so yeah, okay, sorry, I did I make it one? Oh, it should be one. Yeah, so both are data setters. It's in both tensor and it's in the float form. So what you do now is you pass it data set uh, into this data set method. So yeah, this a data. So let's say data set equals. So why this is necessary? Because again, PyTorch it's very specific in what format or in which shape it should be. It has some internal stuff, so it doesn't bother us with all that. So we just have to pass our data set with this module, and it will give us back in the required format. Then you pass it to the data loader. So that would be, let's say, data loader. And here you pass the data set which you want, and I'll say what is batch size in a minute. And yeah, and also let's say shuffle equals true, because it will help the model to learn or generalize faster. Yeah. So after that, now let's build the model. So here, when I say here you saw that, right? This is just a single neuron. So this cannot learn much because since it's a single value, it cannot learn much. For that, what we do is that we get more of these neurons. Again, as I said, the more neurons you have, the more cognitive abilities work. You can do it more efficiently. So, taking the same analogy, let's build that. For that, we'll create a class for that called class.net, and we'll inherit from the module called NN module, and let's initialize this uh, basic Python oops concept. And then we also want to use all the methods of our parent class. So that's why we call the super method, and uh, we want the immediate parent of this net class, because NN module, again, it will have so many inheritances. So for that, we'll pass the arguments as net and the object itself. So, for the syntax goes like this. Um, there is something known as NN dot linear. So, it has something known as okay. So the first one which you imply is that how many parameters it has. So since we are just passing a single number, I'll say it as one, and in the first layer, I want like these neurons. I want, let's say, 64 of them. So that is that, and let me add another layer like this. Uh, and then dot linear. And since this layer 2 comes after layer 1, you have to make sure that the dimensions are proper. This output, so if they are stacked up, this neuron ka output will go to the next neuron's output. So I have to make sure that the dimensions are same. So the same dimension what I have given here, I'll give it here. So that is 64 comma, and I'll just use another neuron again, and there's something known as activation function. I'll show you how that affects our our training. So now let's define the forward method. So basically, this forward method, what it defines is that once I give the input, what's the flow it should follow. So for that, whatever x you have, x, I'll just pass it through self dot layer 1, and this next I'll pass it through the activation function, and okay, and again I'll pass it through the layer 2, and now I'll return this. Mm, invalid syntax. Okay, here I shouldn't. Oh, so to import these, I'll say import torch. This is basically to um, include all the packages. I could say here, instead of this, I could just add torch again here, but that's not usually people. I mean, what the convention is followed. So I'll just again. Oh, I commented this. Yeah. So this is done. Now the training part. So let's go through all the steps which I mentioned. Before that, let's instantiate our class, and then let's define our loss. That will be nn dot msc loss. MSc loss is the mean square error loss. Basically, this equation, it will just take the difference and square it up. That's our loss. And optimizer, what I mean by you saw this, right? Update weights. So actually, this equation, that is what people call as optimizer. So this is a very simple one, just taking the gradients. If you go further, it will not be the simple equation. You'll have something in denominator. You multiply with stuff. Basically, this you can, in layman terms, you can say that this equation will get complex, and for each equation there is a name. So for that, the best equation for that now I can say um, is something known as uh, Adam optimizer. So let's define that. Just have to say torch dot optim dot Adam, and I'll pass all the parameters of the. So basically, this net is that I want all the parameters of this network to be learned, right, which I've instantiated here. So that's why I'm passing this as my parameters. And actually, the syntax is this. Yeah, you don't worry about this now. So learning rate is basically, instead of just grad, I'll multiply something with known as learning rate. So it's again a constant. It could be 1, 2, or what I've defined here, 0.001. So that gradient will be multiplied with 0.001 and then added or subtracted accordingly. So that is learning rate. And mm, what, okay, let it. Mm, there is, yeah. Yeah, yeah. So it's a simple one. So it doesn't have any parameters. That's why I got the error. So now let's actually train this. For that, let's write a for loop, a single one, like how many times. So what I'm defining by this is that how many times do I want my do I want this data set to be passed? So if I say just one, all these will pass through. I mean, the model will get only one chance to see the whole data set. But if I increase the epochs, the number of epochs will be equal to the number of times my network can see the whole data set. So I'll increase it that because just in one go, it will be one epoch, it will be just one step, so it cannot learn much. So you need to pass it again and again. I'm passing it here, 1,000 times here. So first, let us batch X and batch Y. So this hmm. So this data loader is basically an iterator. it will in each iteration it will since I've specified the batch size of 50, it will keep on returning me for 50 set of x and y. So this bx will have 50 examples of x and 50 examples of sin x. That is there. Basically, this is my x and sin x, the initial one. And now what I do is that y predict. So I'll just I'll go through step by step again. I'll pass it to my network, in which is initialized randomly. Okay, now this is just n. I'll pass b comma x, and then what I'll do next is to calculate the loss, right? Let's do that here. Loss is equal to uh, loss of uh, y pred comma y of patch. So here I have my loss, and now it's time to calculate the gradients. That will be yeah, this is one thing you need to be careful about, because in each epoch what happens is the gradients will keep on adding. So you remember x plus y was gradient was 1, and if I run it in a loop 1000 times, that gradient value will become 1000, because in each loop the gradient of x kept on adding. But I don't want that to happen, right? I mean, in each iteration I want like fresh gradients of that particular thing. So I'll just make sure that all the parameters gradients are zero. That after that, I'll do loss dot backward calculating all my gradients, and I'll do up and up step. Basically, it'll this one updation of this w. This is calculated when I mean opt and out step here. So this is for us to see the loss. I mean, so technically, every time the loss should decrease, right? So let's print in every epoch what's the uh, loss for that. And loss of 1, and this is the format method. Um, So this loss dot item will return the value of loss for this. So we can run this, I guess. Hmm, okay, here actually this should by of p now. Okay, so this is p. Yeah, so you can see the training has began, and you can see the initial loss was 0.71 thing, the mean square error thing, and now it has reduced to 0.036727. So, let's actually predict this. Let's see how our model has learned from comparing it with the actual graph. So, for that, I just uh, copied. Okay, until that, you guys have any doubts? So you got all the steps here. Okay. Yeah, here. So any doubts in these code? Why anything in particular works, or why is it this way? Hmm. Any doubts? Um, okay, I guess that's not. So let's plot our prediction and the actual value and see, how it works. So let's say plt dot plot x comma y, and since we'll be plotting it on the same thing, let's give it a label uh, for that, and let's get this here and um, okay. So yeah, so basically the same one. I'm just lazy to type it again. Yeah, so it's the same one. You can see that here. I'll teach you. I'll tell you why the activation function, which I skipped here while explaining, is important. What activation layer does is that it adds non-linearity to your network. So since I have commented this here, you can see it's a straight line. I mean, this is all my network can learn, even if it has let's see the network, even if it has 64 values. But now if I uncomment this, that means I'm including my activation function. You can see that yeah, now you can see that the prediction is much better, right? That's because I think you guys remember that if you add, subtract to do any operation on two linear matrices, or if you do any operation on two linear things, the resultant will also be a linear. That's why it was a straight line. If you don't add activation functions, it will introduce non-linearity. So what I mean is that non-linearity, it will add it will give you curves, or sudden changes in the output. uh, uh, I I guess I think you guys remember the ramp function. Till 0 it will be 0, and then for all the positive values it will be 1. So that is a nonlinear function, right? So ReLU is something like that. It's technically a ramp function. So if I uncomment this, see, now we have some non-linear predictions. So let's increase the number of neurons to 128, and let's see if I get any better results. Yeah, so you can see, right, the prediction and what it has learned is almost the same. As I told, the more the number of neurons, the better it can learn. You can add neurons or more number of layers, or basically stacking these uh, neural neural. If you're stacking it up, then it's in the same layer, If you are passing the output of one neuron to the other neuron, then it is considered as another layer. So um, yeah, so now we can see that the prediction and this thing is almost the same. So just for confirmation, just see, I'll remove this and again it will be a straight line. Because no matter what you do with linear things, it will be, see, it's a linear, it can only learn straight lines. Yeah. So this was all about it actually. Thanks for showing interest and I enjoyed teaching. So hopefully you guys like the session as well.